Welcome to Lecture 16, Design Exercise 5 in Module 3. We will look at a few more problems related to integrating uh, the type of material and the type of shape and the type of loading condition for a given design. So when we are looking at a stiffness limited design in bending, we came across a shape factor phi that was defined as the ratio of the bending stiffness of a target section, such as this tube or this eye section, in reference to a section such as the square shaped cross section that has the overall same cross sectional area. So for the square cross section, the second moment or the area moment is defined as b to the power 4 divided by 12, where b is the length of a given side of the square cross section. So the cross sectional area is b square, and so this initial moment of area for the original section, for the square section, is a square divided by 12. Now if you keep area as a constant and now transform that square cross section to a new shape, the moment of inertia or the area moment, second moment, is divided by this integral of y square times by times dy, right? So this integral over y. The stiffness is proportional to the modulus times the second moment, I. So S is proportional to E times I. So the ratio of the two bending stiffnesses, right? The bending stiffness of the shaped section S to that of the original section, which is a cross-sectional area, square cross-section, S naught, is given by E times I divided by E times I naught. The area is unchanged and the modulus is also unchanged because we're making it out of the same material. So the shape factor for elastic bending for a given material is simply I divided by I0, and this original I is a square by 12, so you have the shape efficiency factor for elastic bending as 12I divided by a square. Let's take a look at what these mean for specific materials, because we haven't yet looked at that. Suppose we consider an I-beam and we have the specific dimensions. H is 3, B is I, and the thickness is 0.125. So phi we can determine as an efficiency factor for the shape as 12I by a square. Now we know that for a square cross section, if B0 is equal to 1, the area is 1. And so if you were to keep the shape, a cross-sectional area the same, then you would expect that for this type of shape, this eye section, which is given by 2 times T times H plus B, because the area is kept constant, what is A? Should be 1. But now, having known the denominator term over here, what is the numerator? I. It's given by this term over here. So if you substitute the terms for H, T, and B, what do you get for I? What do you get for A? A is 4 times 0.125 times 2, and so it's 1. I is 1.125 if you substitute the terms over there. And so phi B for the values of I and A will be 13.5. What does this term mean? It means that for these dimensions of the I-beam, the shape increases stiffness over 13 times using the same amount of material, because cross-sectional area is the same, right? Just the shape is different. This is the indicator of what the shape factor means. The question is, can you make materials with this shape factor, or can you make designs with the shape factor for all materials? Some materials can be cast, some materials can be machined, some materials can be welded together, some can be deformed into given shapes, but not all might be possible, right? For this. So there are limits to which a particular geometry can be made by a given material. And it depends upon the melting point, the mechanical properties, so on. So let's get very specific with the next problem, in that for this I-beam design that we just considered, can you make them from all these different materials? How would you go about answering this question? We had earlier come across the fact that there is an upper limit for a shape factor for a given material, right? For steels, it's a number 65. For aluminum alloys, it's 44. And for woods, it's 6. We came across, for this specific geometry, that is an I-beam with the specific dimensions, that the shape factor was 13.5. If you look at this information over here, you can see that the upper limit for polymers and woods is 6 in bending. That indicates the specific shape cannot be made by these materials. Maybe there's a buckling related issue. So the bottom two are eliminated for this specific geometry from those two materials. Also see that depending upon the loading condition from bending to torsion, the shape efficiency factor limit for a given material changes. That is, the extent to which structural efficiency, that is minimizing mass by changing the material and shape, is more effective in bending than in torsion. That's what you're beginning to see with these types of differences in values. If you look at the property chart of E versus rho, as shown over here, for this material index E to the power half divided by rho, if you look at this as one of the lines, right? What is the slope of this line? It's 2, right? Because it's a log-log plot. Based on the information that we saw, if you can go all the way from 1 to 44 in terms of the shape efficiency factor, you can be able to improve the effective modulus and density to the point where you can create a more effective shape in terms of minimizing mass. And the new material that was created would have modulus of the original modulus E divided by the shape efficiency factor, and the original density rho divided by the shape efficiency factor would be the density of the new material.